Hello everyone, and welcome to the fifth workshop for the Fault2SHA. This workshop this year we're calling All Hands on Deck, Promoting Faults in Seismic Hazard Assessment. So we really are in this meeting trying to encourage us all to collaborate. We're going to start today by going through some of the work the laboratories have already done in Fault2SHA and some of the ongoing work. We'll introduce some projects. And then we're also going to hear from lots of members of Fault2SHA and beyond, looking around the world and at different aspects of Fault2SHA. So I want to say that we are dedicating this workshop to Patience Cowie, and Una will say a word about her in a moment. But first of all, I'd like to hand over to Francesco Vicini, who is my co-host. I should have introduced myself. I'm Joanna Walker, for those of you who don't know me. And I also want to say a quick thank you to Sharang and Claudia, who are working behind the scenes, keeping the meeting going. So thank you very much to them. So at this point, I'm handing over to Francesco, and welcome again. Thank you for joining us all.
Thank you, Joanna. Welcome everyone. First of all, I would like to thank the member of the executive committee, and in particular you, Joanna, for the organization of these workshops. And I would also thank Sharon and Claudia for the technical support. Some quick practical and technical indication. For all, please keep your microphones on mute unless presenting to avoid feedback, and possibly turn off the video. For the presenter, please do turn on your videos while presenting, if possible. And also for the presenter, please stay alert and be ready to start your presentation when prompted. If a presenter will have some internet connection problem, we will carry on with the program. So it is possible that we will have some small amendments on live. So again, please, presenter, be ready to anticipate your thought. The questions can be posted to the chat in the Zoom. There will be someone who will try to collect the questions. Please use the @ and the name of the presenter to indicate to which the presenter the question is, to which presenter you want to post that questions. For those that are following on YouTube and wish to ask questions, we will try to accommodate. If we can, please send an email to the moderator. And in this first session is Bruno Pace. So his email is bruno.pace@uniciacca.it. And before starting with the presentation, I'm inviting Una to say a few words for Patience Cowie. Please, Una, you can go.
I lost the connection for a second there. Starting very well. Huh? So good afternoon, everybody, and thank you all for participating to this extraordinary workshop online. We would have never had so many people if we had been in presence. I would really like to talk to you just a few seconds about my dear friend Patience. She was a good friend for some of us, a great colleague for many, and an inspiring person for all who crossed her path. We will all miss her greatly. Many of you may not know her, but thanks to her open-minded approach to science, she was able to bring innovation in all the research she did, and will undoubtedly be remembered as a great researcher by the earth science community at large. She focused in the most recent years on active tectonics with the main aim of integrating field observation, theory, and numerical modeling. So for many years, she focused actually her studies in the Central Apennines in Italy, setting the building stones of what is today one of the Fault2SHA natural laboratories. Patience was indeed among the promoters of the Fault2SHA working group. Thanks to Patience's effort and passion, she really helped in promoting the first Fault2SHA meeting back in Paris in 2014. She was really convinced that an interaction between geologists and modelers was the best way to go to improve our understanding of earthquake phenomena and mitigate seismic risk. We will be repeating this message throughout the workshop, because of course she was right, and I think we should pursue again along this line. So we are grateful for her enthusiasm. We will continue thanks to her seminal ideas of fault interaction, episodic fault activity, fault propagation, and fault linkage. She was a mentor for most of us, and we will miss her profoundly. So thank you.
Thank you.
Thank
you, Una, for your words. We can start with session 1, that is devoted from the field to the table. Experience gained so far from the Fault2SHA Field Laboratories, and I'm inviting the first presenter of the day. It is Laura Peruzza with the Fault2SHA Laboratories activities. Laura, you have 10 minutes, and I will give you 1 minute left.
Okay, thank you very much. I'm trying to cut off this line of faces that I have on my screen, but no problem anyway. Good afternoon, everybody. I'm Laura Peruzza. I'm talking to you from Trieste, from my home. We are in Italy, in the very, very northeasternmost corner at the border with Slovenia, in yellow COVID zone right now, but we will be orange tomorrow. So enjoy your workshop at distance, and I will be talking about the working group Fault2SHA and the natural laboratories that we state within the working group. First of all, what is a working group Fault2SHA? It is a working group established within the European Seismological Commission. It has been set up for the purpose of studying a particular scientific problem, and our problem is to motivate exchanges between field geologists, fault modelers, and seismic hazard practitioners. You have to remind that the European Seismological Commission does not have a financial support for working groups, so all the activities that we perform are based on voluntary efforts. We started in 2016 at the General Assembly held in Trieste, but the story began before. I remind you that during the very first workshop we had in Paris in 2014, there was Passion. It is the red corner in the light of the first photograph on the left. And she was with us, and it was a pleasure to have her with us. We started so in 2014, we were 10, 12, 15 researchers, basically from 3 countries, Italy, France, and UK. At the establishment of the working group, we were about 70 members of the working group, and they elected an executive committee. You see the faces on the right of the slide. 2 weeks ago, we were 150 members, more or less of more than 30 countries. And we are slowly growing in the size of the members. You will ask yourself why we need an executive committee if we have no fund and no product to deliver. Well, the members of the executive committee are important because they lead the activities that we perform. Behind each person, there is an activity that is led by one of us, and the other of the group are supporting the functioning of the structure. We are reasoning about to enlarge the executive committee in the next year because the group is grown. But on this topic, we will discuss a bit during the 3rd day of the workshop on December the 2nd. The topic will be the working group structure. So remind this topic if you are interested in learning some more. The activities that the working group is doing are essentially special session at conferences, publication, special issues, workshop. The one we are doing now is the 5th, as I said before. There are training and tools that are shared in a different way. There are proposals to be written, and we did a lot of proposals with some results, but we can grow on that too. We have the natural labs, that is the topic of my talk. So what is a natural lab in general? Well, a natural lab is a place where you can learn something that cannot be observed elsewhere, or you can imagine the natural lab as a place where you can share and comprehend the causes and effects of natural phenomena, or again, more in a more limited space, a place where you can grow in knowledges, ideas, prototypes, and models, remedies, whatever you want. Well, usually these kind of labs are supported by a lot of money, and we do not have money. So in the Fault2SHA perspective, what is a natural lab? In our opinion, a natural lab is of course a place, but a place where some question can be approached, where some active faults, more or less studied, are present, where there is a seismic risk potential. Be careful, I'm referring to seismic risk, not necessarily seismic hazard, because also a magnitude 4.5 earthquake can have a relevant risk potential, even if in terms of hazard it is not so important. A place where researchers with different background and expertise are available to exchange ideas, to learn, share, and grow. So in the Fault2SHA perspective, natural laboratories are places, of course, but more than that are person faces. And you see here some of the faces that belong to the two active natural labs we have right now. How can I move this stuff out of the screen? Well, the composition is different in the two groups. The list of names is long, and it is becoming longer day by day. We have to find a way to cut the double name of the Spanish guy. You have extraordinarily long names. The two natural labs actually active are in central Italy, central Apennines, and the Baltics. We are in active shallow region. We have a slowly deforming area. We have extension-based tectonics in central Apennines. We have mostly compressional transcurrent frame in southern Spain, but in both the national labs, the idea is to gather data, to share data, to compare the methodological approach that are used, and to have a transdisciplinary approach to learn, grow, and share. If we go back to the field, to the composition of the two groups, we can reckon that in Spain we have mainly geologic expertise component the group, while in Central Apennines we have half and half hazard modelers and geologists, let's say. And I interpret these differences as a different maturity of the studies we have in the target area. The question to be approached are different, and there are different opportunities to broaden the collaboration. As well, there are different hazard and risk levels in the two regions. As I'm old enough, I was in the team that started more than 20 years ago with the parameterization of the seismic of active faulting in the frame of a seismic hazard assessment. These are volumes that has been released in the aftermath of the Colfiorito Celano earthquake, 1997-1998. And at that time, the group was essentially a national group of geologists like we have now in the Baltics. So since then, in central Italy, we have had different ideas growing, different, let's say, debates, discussions, sometimes hard discussion, different models to be promoted for modeling faults in SHA. And well, there is only a super short list of papers here, because then we had the L'Aquila earthquakes and the 2016 Norcia Matrice Viso sequences that gave an incredible an incredible increase in the studies and in the number of people that were working on that area.
1 minute left, Laura.
So now we have a collaboration that is between different teams, Italy, France, and the United Kingdom, and we have many details in the following presentation. And the list of common publication that we are doing together is growing. And well, Joanna, when we were preparing this workshop, said, I've never published anything with any of you before. And so this is an extra reason to start thinking in joining one existing natural lab or establishing a new one. Now I can say, enjoy the following presentation, and I'm done. Thank you.
Thank you, Lara. Thank you also for being time. I'm inviting the next presenter. She's Joanna for worker with the Central Apennines Laboratory and a focus on the database in Central Apennines.
Hello, so I'm going to be presenting one of the outputs from the Central Apennines Laboratory. This is one of the 2 laboratories we have that Laura has just been introducing. So today I'm going to talk specifically about the Fault2SHA Central Apennines database and how we go about presenting geological data for use in seismic hazard assessment. At previous Fault2SHA workshops and in other conferences, the use of faults in seismic hazard assessment is obviously being recognized, hence why we have the Fault2SHA working group. But also we're recognizing that as we develop more tools, open source tools and other tools, and as we recognize the need for detailed measurements and for having lots of data, we realize we need a way of sharing that data and displaying that data such that it can both be easily incorporated into models, hazard models and risk models, but also so that it can be understood. And a key point here is we need to show and be honest about uncertainties, unknowns, where there's agreement in the community, where there isn't agreement, and so forth. And so we hope we've developed a database structure that does address these various issues. So in terms of the fault map, as Laura introduced, we have teams from Italy, from France, and from the UK, and we had different research teams working in this area. And we really wanted to bring them together and make sure we could see that how are our maps different? How are they similar? Are the differences due to genuine scientific differences of opinion, or is it more to do with that we just haven't done so much work in a particular area? So do we have fundamental differences, or are the differences there for other reasons? And what we've actually found is we agree on most of the locations of where the faults are. Where we did have discrepancies, this was mostly due to the detail of mapping or the areas where we had done more or less research. And then there were a few areas where we needed improvement. And we made quite a few of these improvements through our work for Fault2SHA. And we've also identified areas where we think even more improvements could be made. So in terms of how we present the database, we in particular really noticed that something we wanted to do was to look at how we should present the data. What scale should we present the maps at? Because there are lots of databases out there. There are lots of useful fault maps out there. But a question of scale and how we go from geological observations or fieldwork observations at very, very high resolution to then how do we incorporate this into seismic hazard modeling? What scale is useful? And it's easy to either go in a very, very detailed way, which is then very difficult for a modeler to extract, or to simplify too much when actually as models develop and they can cope with more data, we've simplified it too far. So we've come up with a system, and it's, it is complementary to other systems that have been developed, but it was really developed through this collaboration in one of these natural labs. In the room, we had people who were in the field collecting the data. We had people who use the data, who calculate slip rates, and we had seismic hazard modelers. And it was this combination of people together that helped us come to, I think, a great solution in terms of having both the data displayed in high detail, but also in such a way that modelers know what uncertainties there are and how they should include it in models. So we show here that we start, our primary data is shown at the trace level. And this is all about how we have observed things in the fields. So the length of a trace is just defined by how far in the field or how far in our mapping we have a particular location certainty and activity certainty. And I'll talk more about the location and activity certainties later. So wherever we have a set of observations, and we use a very wide range of observations, both in terms of field work, where we can identify scarps, where we have dated offsets, where we have subsurface geophysics data, if we have paleoseismic data, if we have real earthquake offsets, lots of different data we use to define this. So for how far we have the same data, for how far we have the same certainty in location and the same certainty activity is how far we define a trace. So these are very detailed high-level mapping, and it's primary data, primary observations from the field. We then go to our next resolution, which is a fault. And this is how we connect the traces. So we know how these traces should connect, but remember the trace has been defined by our own observations, whereas the fault is defined using geological parameters. So where is the fault behaving? Sometimes we simplify the traces. So for example, if we have synthetic or antithetic structures, we will simplify these at the scale of the fault, where we think these are connected. At the fault level, we define a single activity scale and a single location scale. So when we're going from trace to fault level, we will adopt the highest activity among the traces and the lowest activity among the locations. And I will come back to that in a moment. We then go one step further from faults up to master faults. Now, master faults in some cases are the same maps as the faults, but there are cases where we have faults defined through the literature, or faults which are offsets from each other at the surface, but we think are behaving as one master fault at depth. And so at the step from fault to master fault, there is some interpretation. It's based on geological rules and it's based on scientific principles, but there is some interpretation when going from fault to master fault. So let's have a look at what these maps look like. So here we show for the Central Apennines, our laboratory region, the traces map, and you can see how we have different thicknesses of lines representing the different location certainties and different colors representing the different activities. It's a detailed map and it's showing all our primary observations. Once we go up to the fault level, it's slightly simpler. We've connected the traces, and as mentioned, we have the same activity and same location scale for a single fault. We then take the fault map and we can then convert this to the master fault map, which is again a slightly simpler map than what we saw at the fault scale. And these different levels mean that we can see the primary data and we can see the primary mapping that has been done, and we can go from them and actually see how these have been combined into faults and master faults. So if somebody wants to use, for example, master faults to do hazard mapping or hazard calculations, they can see what observations have gone into our definitions of location certainty, activity certainty, and how we have combined these traces. So the idea here is modelers can see where the information is coming from, but at the same time, we're not just producing a very detailed trace map, which is very difficult for modelers then to combine without help from the geological community. So in terms of this location scale and activity scale, these are similar scales to what others have done before, but we've defined them in a specific scale here. So we start off from 1 and go down to 4. 1 is the highest location certainty, 4 is the lowest location certainty. So at 1, we really are saying the location is certain. So this is where we can map the trace. We might have a bedrock scarp in the central Apennines. We might have several trench sites which can be connected at high resolution. We may have real-time earthquake ruptures that show us exactly where the fault is. So this is where we really do know the fault trace within a few meters. We then go down to location 2. So this is where the trace is known in a few or maybe tens of meters, but there might be small alterations that are possible. We may have, for example, single point data through dating, whether that be paleoseismic dating, or we might have some geophysical data at single points, but we might have to interpolate between these points. We might have a scarp at the surface, but that needs interpolating to see exactly where it goes. So again, we know, at a larger scale, we know where the fault is, but there might be some small alterations in the high detail of the traces. When we go down to 3, again, we're just stepping down a location certainty here. So we know the approximate path, but perhaps we don't have that exact trace known. So we could move within a few or tens of meters from where we've drawn it. So what we're saying here is new evidence could actually provide some changes in the maps drawn. And then when we get down to 4, we say that location is uncertain. We might know the fault is there, but we don't know its exact location within tens or perhaps up to 100 meters or so, but more likely we're out by up to tens of meters. So this is just showing you some of the techniques we can use to define exactly where the fault is. We might look at scarps at the surface. We can use digital elevation models, aerial photographs, real mapping in the field, earthquake ruptures, geomorphology, trenches, geophysical data. There's a lot of data we've used from a wide range of literature, as well as our own independent mapping for this project as well. When it comes to activity, we note that activity is something which has a definition. If we talk about an active fault, this can actually mean different things in different regions. In some areas, it might be 12,000 years in that there's been activity on the fault in order to define it as active, whereas in some regions, it might be 125,000 years that needs to be used to define whether a fault is active. So if it's had activity in that time, it would be declared as active or not. We wanted to move away from saying active fault or not active faults and provide a bit more uncertainty about this and a bit more clarity about what exactly we meant in our scales in this database. In the Central Apennines, the time period we chose was to look at the late Pleistocene Holocene, so the last 15,000 years or last 12 to 18,000 years. So how certain are we of activity in that time? So at scale 1, again, 1 being the highest, and we go down to 4 being the lowest level of certainty. At 1, we have to have a dated offset on that trace. So, and that means that the actual dating needs to be done on that trace. So we might have a paleoseismic trench, we might have cosmogenic data, which either of these could indicate activity in this time period, or we may have real-time earthquake ruptures, either identified at the surface or through INSAR, something like that. But we need to know there's definitely been activity in that time and with a date on that particular trace or at fault or master fault level. At level 2, we still need a dated offset, but the date itself might not come from that specific location. The dating could be a regional dating marker, such as a geomorphic marker. So in the Apennines, we actually have surfaces that were formed during the last glacial maximum. So offsets of these surfaces could be used to indicate a level 2. At level 3 activity scale, there is evidence, there's geological evidence of sort of a longer term offset, so perhaps on the middle Pleistocene deposits, or we may also know that this is a continuation of the same fault or master fault, where another trace may have a dated offset, but we just don't have it on this section. So that's another example where we would have activity level 3. And then down at 4 is where there is geological evidence of offsets, but we don't have it dated to the late Pleistocene or Holocene. So that gives us an idea of our activity. And again, here are just some of the techniques that can be used, whether it be cosmogenic dating, dating in paleoseismic trenches, real-time earthquake offsets, or at level 2 offsets of regional markers. When we went from traces up to faults to master faults, as a group, we looked at the different evidence. We obviously used a lot of the data in the literature. This is a very well-studied region. And what we looked at here in particular was trying to work out what agreement there was, or whether there was conflicting evidence of how these faults could be connected. And overall, we found that it was easy to go from faults up to master faults to know how faults are connected. But we did have 3 examples where actually we felt that as a group, we couldn't be certain how the faults connected to form these master faults. And it happened that we had these 3 examples, and for each we came out with 2 different possibilities, depending on which observations and which evidence you used. So within the structure of our database, there is the possibility to show that there is uncertainty how these faults are connected. And we think this is important because this is a real problem. It's easy to go for one interpretation and offer that to modelers, but actually there might be uncertainty at that basic level before any of the seismic hazard calculations have actually started. So we wanted to be able to show that uncertainty. So by allowing for there to be different options, allowing for different master fault interpretations means that modelers can then take those different interpretations and use that uncertainty. So here are 3 examples. I know there's quite a lot of detail. I'm just going to zoom in on one of them. This is an example from the Ficino Basin. For those of you less familiar with the region, this is right in the middle of the region of the Central Apennines region. And the Ficino Fault is where the 1915 earthquake that killed 33,000 people occurred. So this is a really important area. It also has evidence of a high slip rate, among the highest slip rates in the region. So it is important to try and know exactly how this fault connects at depth and how the master faults are arranged here. And we ultimately came out with 2 different interpretations. There are people who strongly believe one way or another way, and there are those who aren't sure either way. So as a group, we did decide that we should show both these interpretations. And that's similar for 2 other examples that we have as well. I'm not going to go into all the details of the different evidence for these different interpretations here. I can discuss those with you another time. What I really want to emphasize today is that there are differences in interpretations. Different evidence can sometimes lead to different interpretations. Most of the time, we found agreement. Most of the time, we can use different evidence and it can work together to show what the fault map and master fault map should look like. But there are places where there's genuine uncertainty. And that's okay. We can take that uncertainty and show it in our maps. And that's really important because then as more evidence comes, we can either use this to update our interpretations or to show that there really is uncertainty. And as hazard models develop, they can cope with this uncertainty. And I think there's been a bit of a tradition with fault maps to really try and come out with one answer or really try and go with our best guess. But actually showing this uncertainty is helpful to the hazard modelers. It means they can look at different configurations. They can look at different rupture possibilities, and we can map that uncertainty. So again, our database structure is designed to try and be honest about the uncertainty that there is in our fault maps. So what does this database structure look like? We have at the center of it all, at the center of the whole database are these traces. And as I say, this is where all the primary data is defined. And at the trace level, we show in our database, I'll show you an example later, but we show all the different observations that have been used to define our activity scale and to define our location certainty as well. So it's at the trace level is how we record all the observations that have gone into defining those certainties. And it's worth pointing out here that this structure can be adapted to other regions. It might be that the observations we're including for the Central Apennines are directly applicable, or it might be that there are additional features that you want to include. We can do that. That's manageable. So at the center of our database are these traces, and then we can see that they can be joined together and accommodated into faults, And then the faults themselves can be accommodated into master faults. As I say, sometimes there is a one-to-one mapping of fault to master fault, whereas sometimes there might be several faults forming a master fault. And within the master faults, we have this master fault selection, which means you can choose how you think the fault should be configured into master faults. So we suggest the different options, but these different options can be interrogated by modelers in order to explore uncertainty. Connected to the trace, we have the trace location and trace activity. And we mentioned, how we define those at the trace level. In terms of going from trace to fault to master fault, for activity, we go with the highest level. So if we have 3 different traces forming a fault, if one of those traces has activity certainty 1, at the fault level, we would assign it an activity certainty 1, because we say, we know there have been earthquakes on that trace, so therefore we can assume that the whole fault is capable of hosting earthquakes, and similar for the master fault. Now, obviously, we assume that all the traces and all the faults and the master faults in our map are capable of hosting earthquakes. What I mean there is just saying what evidence we have actually had at the trace level, we can apply to the higher levels as well. In terms of location certainty, we go with the lowest level. So if there's any part of the fault, or up to master fault as well, which has a lower location certainty, so for example, if we have down to a level 4, usually it's at the tips of the faults, then when we show the fault and master fault, that would be defined by that lowest level of location certainty, so 4 in that case. We then also have our slip rate data and our local geometry and kinematics data. So this includes offsets, whether that be measured as throw or slip originally. We can then transfer between the two. We look at the dating period that's been used. So if we have a throw, over what dating period is that throw measured, or likewise with slip, in order to infer slip rates. And we look at minimum and maximum and preferred values there. So we can look at, again, the uncertainties and where they are coming from. Are they coming from the dating? Are they coming from uncertainty in the measurements themselves? In terms of the local geometry and kinematics, we look at the local strike, dip, and these are measured as point data. So it's specific points that we can define on a map. So any data that's included in this database has a very specific GPS location. And that's important so that later when modelers want to come and interpolate the data, they know exactly where this data has been measured. So I mentioned we have the local strike at the surface, the dip at the surface, slip vector azimuth, slip vector plunge, and we're also looking at other features as well. We also have earthquakes data. This is an area we want to expand. So where have we got paleoseismic trenches or cosmogenic?
3 minutes for you, Joanna, sorry.
Thank you. And also where we have real-time earthquake ruptures so that we can see what's going on there. And then we have some support tables which show you where we've got the data, so the references, the techniques used, and the coordinate system used. So in terms of the structure, each of these tables has a lot of data in it. We define for the master faults, we show how we've got the configuration going. At the fault, we have looking at which master fault the faults belongs to, and this is a dynamic field. So any fields showing in red here are dynamic. They will depend on the master fault selection chosen. We have data that's calculated automatically in the database, so that's shown in blue, so the location scale, the activity scale, and this is built up from the location certainty and activity certainty from the traces, and then we have input data as well. So this is how it looks in terms of the master fault selection. I'm just showing an example here. We can choose A1, or if we click the button, we can choose A2, and that will alter any of the red values in the tables. So this is how the fault table looks like. As you can see, it's easy to use. It's available in Excel. It's also available in QGIS and other GIS programs if wanted. In terms of the data for traces, I'm not expecting you to be able to read every line here, but as I mentioned, the idea here is it's using all the different data, so all the different observations, and we just say yes or no, whether it's been observed on that trace to help build up that activity and location certainty. We also have the maps available in GIS, so you can get towards all the data, and in Google Earth as well. And you can just click on the faults, click on the master faults, click on the traces, and get all that information in the tables available to you. So that showed you the tables of what's in the map data. We also then have all the information available in the slip rate, local kinematic, local geometry and kinematics, and the earthquake tables as well. So a lot of data in there is recorded. So you can see where all the information is coming from. And again, this is all available in GIS as well, and in Google Earth. We also have these support tables, which are just really reference tables, so you know where the information is coming from, so you can go back and look at the primary data if desired. We're having all this data available means you can do lots of tests, and you can start to interrogate the data. Here's just a couple of examples where we looked at things like the length distribution of the master faults, the maximum throw distributions, and how the maximum slip rates and maximum throw rates correlate with the length of the master faults. We can also do a similar exercise looking at the slip vector azimuths, looking at the fault dips and plunges of a strike slip vectors. So having this data in this way also allows you to interrogate the data. So ultimately, what are we trying to do? What are we trying to achieve? We're trying to show an open access database that anyone can interrogate. You can see where the information comes from. You can see how we've gone from trace to fault to master fault. You can see the primary data in the traces and then follow the interpolations through up to master fault, which might be used in the modeling. We also have the slip rate and local surface geometry data, all at point level data. So it's anywhere it's at a very specific location. It's not just a general result for the whole fault, because we know you need detailed information. Otherwise, we'll get very large uncertainties or even errors in our calculations. In terms of how we then use these master faults, I mean, a modeler doesn't need to use master faults. They could go down to the fault or trace level if they wanted. But in terms of how we use them and how we connect them for hazard modeling, really is then a question for the modelers. So the database provides the primary data and any interpretations, but the modelers can go forth and really then decide how to put this data into their databases. And that applies to both the maps and things like the slip rate profiling. And Una Scotti will be speaking next, actually taking this data and showing how we are doing seismic hazard calculations with it. So thank you very much. I hope this is a useful resource. It should be available through open access soon. And I also want to make the point that this is a collaborative work and we welcome future collaborations. If you have data you want to include, please get in touch, or else if you want to take this structure and apply it to different regions, again, please do get in contact, because this should be used as a starting point for Fault2SHA databases. So thank you very much, and I will pass over to Una.
Thank you, Joanna. So we can move to the next presentation by Una Scotti. Una, do you have, please remember you have 20 minutes, so I will notify you when there are 3 minutes left. Okay.
Okay, do you see my presentation?
Yes.
Okay, so good afternoon again to everybody. So I'm following up on what Joanna just presented very nicely, is the second part of the story. How do we use this data in such a way that we can easily compute fault models that we can use for hazard and risk estimates? So just to remind you, the classical approach to seismic hazard is still today for many regions of the world based on just seismicity. So what you do is you draw a region, a tectonic zone that you think is homogeneous in terms of seismicity rates. You compute those rates, and then you come out with a single frequency magnitude distribution for the whole zone. And that will produce for that particular tectonic zone a homogeneous seismic potential. So here what you see is the seismicity rates of this region taken from the Italian catalog, where we have actually explored uncertainty in the completeness time and magnitude estimates. That's why you see the gray region. What we're trying to do is to go from the slip rate data points that are available today in the Fault2SHA database, and then produce multiple frequency magnitude distributions that reflect the activity that the geologists see in the field. And that, of course, has been possible only thanks to the Fault2SHA working group, where we have had a consistent exchange of information throughout the. Do you see my full screen? Yeah, or is this thing is maybe down here? And then we also had the Sheriff's tool that some of you may know, which is a user-friendly method that converts slip rates into seismicity rates. And this was developed and shared by Thomas Chartier, who did it during his PhD thesis. So honestly, without these two, we would not have been where we are today. So what we did during the Fault2SHA database construction, we really interacted, and Joanna just told you that we have come up with this master fault concept, which is a geological object, we believe representative of the geologist's view of how traces mapped at the surface may connect at depth. And she also told you that there are a few options. So for this, the remainder of this talk, I will just call on option A1, B1, C1, because the idea of this talk is just to illustrate how we can go for a given option from the database to the hazard and risk estimates. So the first hypothesis that we need to make is, okay, we have a master fault and we have many data points. What do? We do a constant slip rate value all across the master fault, which is usually what it's done because we're also lucky to have just one data point most of the time. But then we came back to geologists and said, maybe we should do a geological assumption, insisting on this concept of master fault and build our slip rate profiles, assuming zero slip rate at the either end of the master fault. And so this is what we are going to be looking at in terms of results. The second step concerns the modeling assumptions mainly. Gosh, I have all these things coming in. So the first thing we need to do is to consider slip rate profiles, is to subdivide the sections into 10-kilometer long sections. This concept was developed from the USERF3 modeling approach. It allows to consider slip rate variability along the master faults, and it allows to consider also, as you will see in a second, multifault ruptures. So basically what we're doing now, it's an additional simplification. For each section, we take from the profile the mean value in order to try to follow as best as possible the variability along the master fault. Now the sections we can combine and make complex multi-fault ruptures. And in fact, they can jump from one master fault section to another. In this particular talk, you will see results just based on a very simple criteria that as long as sections are less than 5 kilometers apart from each other, then they can be a part of a single rupture. Other criteria, of course, could be imagined. And of course, in the future, it will be nice to have the insight from physics-based models and earthquake geologists to make sure that we cover all the physically possible and geologically documented complex earthquake ruptures. So the final ingredient that we need before we perform hazard calculations is the 3D geometry of the fault. Today, what you will see is based just on a very simple idea. The surface geometry is projected to the bottom of seismogenic depth along the average depth of each section. So basically, here we are. We went from the database, constructed the slip profiles, attributed a slip rate to each section. We have a list of possible earthquake ruptures. And now we are ready to run the SHARIFs. SHARIF stands for Seismic Hazard and Earthquake Rate in Fault Systems. And it's an iterative approach that converts increments of slip rates of each section involved in a rupture scenario into earthquake rates. And it includes off-fault seismicity and epistemic uncertainties. But today I will just run the model just on the faults. I will not talk about off-fault seismicity, and I will not talk about epistemic uncertainties. Again, the idea is that we show you how we can go from the data in the field to the hazard and risk estimate. It does require to assume a shape for the magnitude frequency distribution, which needs to be defined at the scale of the region of study. So for this exercise, we relied on the shape of the catalog for this region that I just showed you, and reproduce. The idea is that we produce earthquake rates along the different faults that collectively will have this shape in the frequency magnitude distribution space. So off we go, we run SHARIF, and let's check what SHARIF comes up with. Well, SHARIF's earthquake rates, which are now based only on the mean slip rate estimates of each section, no epistemic uncertainty was performed here. This is what they come up with. And when we saw this result, we were really amazed because we did the only big hypothesis, as I showed you, was the slip rate profiles and simplifications on how to attribute slip rates to sections. Everything else comes straight from the database. And so I think for today's talk, in any case, we could discuss about the fact that we're producing maybe more seismicity for lower magnitude events, but we're doing pretty well for higher magnitude events. But today, the idea is to go all the way to the end of the chain of calculations so that you can appreciate the value of what we've done. We can also check at the level of a single master fault where we have paleoseismological data. How does it compare? So here you see it. We are on the Montevideo section number 55, and this is what SHARIF calculates for this section, based on the different hypotheses. And an important hypothesis, as I said, is the seismogenic thickness. So here you have the evaluation for a 50-kilometer seismogenic thickness. It's a little bit high if we compare it to the paleoseismological data that has been published for this section. So if we introduce a 10-kilometer seismogenic thickness, it looks like we're doing a better job. So this is what we'll be showing results relying on the 10-kilometer seismogenic thickness hypothesis for the rest of the talk. And so now we are ready to actually go to the next step and use OpenQuake. OpenQuake, I think most of you should know about, but if you don't, you should. It's a great open source code that allows to go from fault models in which we have seismicity rates for each model to hazard calculations. So we went from master faults to sections and slip rates for sections. And for each sections, we have our frequency magnitude distribution. And now what we need before we can compute hazard is ground motion prediction equations. That is, we need to understand for a given magnitude at a given distance, what is the probability of exceeding a given ground motion level. So plug that into OpenQuake, an outcome for every section that we have in our fault model, the hazard curves for each section. So this is an example of the hazard curves for the L'Aquila locality. And you can see up here, this is the total hazard curve, which is the sum of all the individual sections. And while there are many ways that we can visualize hazard results, it's always sort of problematic. So here I will go through a few examples. Often people would like to see maps. So to what we need to do to view a map of hazard, we need to fix the annual probability of exceedance that we've just computed, and then read off here the PGA value for the corresponding locality. So you do this for all the localities, and here every dot represents a locality in the region, L'Aquila being here in the center. And so you can visualize for a fixed exceedance period the actual values of the PGA level. What you see is that seismic hazard is very heterogeneous across the region, varies considerably between 0.2 and 0.4 G. And that, of course, higher seismic hazard levels are in the western sector, closer to the faults that have slip rates exceeding 1 millimeter per year. Another way maybe of trying to understand the results, it's always difficult to say, well, at L'Aquila, why my PGA is so high at L'Aquila? Let's go and check all the sections that contribute to the hazard at L'Aquila. So this is a sort of a new visualization scheme that we came up with. I decided yesterday that I would call it a hazardgram, but maybe Francesco does not agree. The idea here is that you can visualize the participation of each section to the hazard in the city of L'Aquila. So you can see, for example, that the Fucino in the Lipezza section that Joanna was talking about previously is actually contributing to the low levels of hazard. Whereas when you go to other faults like Barisciano or Sergi, they are the biggest contributors for high levels of hazard. So let's go and see a map of these faults, where they are and how they contribute to this PGA level of 0.866. So this is an additional new sort of visualization scheme that we believe can sort of immediately give you an idea of what are the faults and the sections that contribute the most and the one that you have to worry the most if it's a hazard at L'Aquila that you are concerned about. You can see that that the closest sections to the city of L'Aquila are again Barisciano and Sergi, and they are the ones to worry the most. But however, the high slip rate sections further away do contribute. And so they need to be studied as well. Finally, let's go to step 6. And you can see now it's sort of a very simplified risk calculation that we're doing here. We call it typological risk because we're only looking at the risk due to a single building, a single 2-story masonry house. And so to understand how to compute risk, you need to understand the fragility curves. So the fragility curves represent the probability of exceeding various damage states for specific levels of ground motion intensity. We are going to consider PGA. And for specific building typologies. Okay, so we will just show results for this complete damage or collapse state. But we could do computations for other states as well. The idea is just to illustrate to you how do we do this? Again, we use OpenQuake, and we feed to OpenQuake the hazard curves, and then OpenQuake convolves it with the fragility curves that we provide to result in this annual probability of collapse maps that can immediately tell you that all the localities close to Fucino in the Lipezza and the Liri fault are actually the localities that are more at risk for this in this region. So Now, again, maybe I forgot to say, but the width of the section is proportional to the participation of that section to the risk at L'Aquila. Again, we see a little bit of the same picture. High slip rate sections further away from L'Aquila, here named number 25, is still a concern for L'Aquila. The interest of looking at the risk part of the story is that you have sort of an integration of the hazard curves from the low levels to the high level. So
sorry, Una, do you have still 3 minutes?
Okay, well, I'm pretty much done. Because the main point is that, okay, it's all very nice. We have this database. We made a certain number of assumptions, and we've come up with a risk, typological risk map for L'Aquila. But let's go back to our data and the famous data points that Joanna was talking about. How many data do we really have behind each of these sections? And then you see that we really have very little data for the sections that matter the most for the risk at L'Aquila. So there is still a lot of work to do, but my takeaway message is mainly directed to geologists. Do build a database, do use Fault2SHA tools, and then go and focus on collecting key data that matter the most. This is sort of a closing the loop, I call it, between fault data providers and SHA users, end users. Yes, I mean, this was a methodological talk. I completely ignored the uncertainties. We still need to work on propagating uncertainties properly. There are many different uncertainties to propagate in our seismic hazard and risk assessment methodology. And so we will continue the constructive feedback between data providers and PSHA modelers. But we also wish to connect with other communities to better constrain seismogenic depth, to tackle seismic components, time-dependent models, and physics-based approaches. So in conclusion, we think we have made a fair amount of progress in fault-based CHF, that this can be achieved through interaction and sharing between our communities involved. Develop databases in collaboration with SHA modelers, develop tools and methods that non-SHA modelers can easily use. This is my sort of objective. Hopefully, I get more and more geologists to really use these tools because it helps them understand what the data they are collecting is used for in SHA. And of course, ensure that fault-based SHA results and the shortcomings are well understood. So thank you very much for your attention.
Thank you, Una. Thank you very much for your presentation. I'm inviting the next presenter. She's Maria, and she will present the activities of the Fault2SHA Synthetics laboratory. Maria, do you have 10 minutes? So I will notify you when 1 minute left.
Okay. So I'm sharing my screen. You can see it. Okay, I'm gonna try to give you a general idea of what is the Synthetics Lab. Well, the co-authors here represent the group of people that we met for the first time in 2017, but of course there are many others. Laura already talked about the group, but I would like to add that we are interacting. We have a close collaboration with some other people in the Fault2SHA group, and this has been really fruitful, and I think is the way to continue. So it's something to take into account, that the idea of the network is to include more people and interact with all people that can provide ideas and methods. So the steps we took until now. We started from we assisted to we were in the third Fault2SHA workshop, 3 of us, Octavi, Julian and me, and there we proposed to use the data from the Eastern Betics shear zone as data that can use to test, check, and can be useful in the Fault2SHA tools. So we started with this proposal, and we convinced a group of people to assist to the working session of the first Eastern Helvetic Fault2SHA workshop in Madrid. So that was 2 days of work, 2 days of work that helped a lot to structure the work we've been doing in the later years, and the ideas that mean to set up a laboratory, a Fault2SHA laboratory, and to include faults in the SHA models, because we were really like in giving the first steps. We can be considered a junior laboratory compared to the Central Apennines. So we met later in the fourth Fault2SHA workshop in Barcelona, and the idea was to meet again in a workshop of the group in the Geological Congress of Spain in July, but it was cancelled because of the pandemic. So we are planning to have a meeting in the next month, an online meeting, to retake some of the work, some 3 years after, let's say. Let's see where are the Eastern Betics. So the area, as you see here, is in the southeastern part of the Iberian Peninsula. It's one of the most seismically active areas of the Western Mediterranean. And if we zoom in this zone, we see that there is a bunch of active faults identified. All the faults in gray and also in red are part of the active fault database of the Geological Institute. Well, they are acknowledged there, but we decided to focus, to start up with this system that is called the Eastern Betic Shear Zone. Still, I have to say that it's a debated issue, because how do we define a fault system? And here you see how there are many other faults that are really close to these 6 major faults that probably interact and are in connection, are connected to this system. But in any case, it's a geological system defined because these are faults that present a continuity, mainly strike-slip faults, and with a clear geomorphological expression. So we decided to focus, to start the experiments, let's say, with this fault system. Which geological features make challenging this approach? So this area have moderate and slow slip rates. We are realizing now that probably not so slow as we used to think some years ago. But this makes difficult to geologically constrain some parameters, as it is, for instance, the largest earthquake that probably we never experienced in the history. Who knows? But we are thinking now that maybe a large earthquake rupturing all the system can happen one day. Also, the earthquakes represented in the historical catalog, we see already that doesn't match with the ones in the paleoseismology. But the paleoseismic analysis don't let still control all the events or have a really good constrained paleoearthquake chronology. So the recurrence and many data have a lot of uncertainties. It's a complex system, and the kinematics and the behavior of the system are complex because of the architecture, the number of faults and the location of these faults, and also the geometries on depths are still unknown. There are very few seismic profiles are in-depth data still. So in the first workshop, we were doing some training in Fault2SHA tools. Well, some of these were in the workshop, some are later. But in any case, we discuss about the need to have a rich database, and that need to be improved, in which we need to clarify the segmentation rules we are going to use that control the fault interaction and the triggering relationships. Also, which scaling relationships we were going to use, and very important, the impact of the uncertainties. So to have like an idea, to be conscient that the uncertainties may have a really large impact or not in the SHA studies. So also the need to define the slip rates and the geometry of the faults. So all of this is needed for something that is a key issue, that is the rupturing model that we are using in our SHA models. We realized that we had a long walk to walk, let's say, but it started working. So in the presentation, I'm gonna show you some results of the steps to improve this key input data, and also some of the Fault2SHA models that are already being produced. But this has not been like first the gathering of input data and then the models, but we are doing all together, let's say. So concerning the input data, the propagation of uncertainties, in the last years, we realized how important it is. So now the application of the Sekar and Frankel approach to define the uncertainties and to calculate and communicate the uncertainties associated to the slip rates is now a common practice. There are some PhDs like the one of Raquel Martín Banda, the one ongoing of Paula Herrero Barbero, and the one of, well, some of us in the group that are taking into account this propagation of uncertainties. That means that we don't get the slip rates just but by dividing also the slip and the age of our data. Also, when we obtain the slip rates, when we obtain the slip, we can see and try to define how this varies with time. For instance, one of the most challenging work we done in the last year was trying to define this slip uncertainty and variation in 3D trenching. And we see here how the channels that are displayed in a different way, depending on the age, but also having different uncertainties related. Another handicap is the gaps of knowledge that we have in the system. So this system is made of 6 major fault zones, but in some of these faults, there was an important lack of knowledge that little step by step is being filled up. For instance, the northern part of the Alhama de Murcia fault.
Sorry, Maria, 1 minute.
1 minute? So I will go gaps in, oh, sorry. So also the slip rate divided from geodetical data helps to know how these slip rates varies in time. This is also an approach trying to define the slip variation in time and also in time in space. And finally, the constraint of the earthquake chronologies, obtaining data of larger trenches and also combining many types of chronological data using statistical approaches. So just to finish, also microtectonics also helps, and in-depth data. Okay, so many studies that we have to focus now in knowing the geometry on in-depth. Now, this is just a presentation of what is coming now, because these authors are presenting their works, their results of integrating this geological data in models, SHA models. Octavi is going to show this in the next minutes. And also Paula Herrero and José Antonio Álvarez are going to present the results of physics-based earthquake simulators applied to this. So just the last slide, the take-home message of if you are at home, the message directly. If you want to start a new lab, as we did, take in mind that it's a collaborative work that helps a lot to create community also. Even if your data are incomplete, it's still really meaningful, because these approaches help you to identify the areas that are having a larger impact in the models, and also guide the field work. So helps to define which things have to be better constrained. Okay, so that's all. Can we include faults in SHA? Yes, we can.
Thank you, Maria. Now we have 10 minutes break. Please do not leave the meeting during the break, and be on time, because at 15:30 we will start with the first presentation by Giorgi Casarazze. Thank you. See you later.
For the benefit of those on YouTube, we will stop the stream and then start